This is our first lecture on section 3.4 entitled Ordering Relations. In this part, we talk about the definition of a partial order and a linear order, and we give a few examples. So here's our definition of a partial order on a set. We start with a set A, and we let R be some relation on A. We say that R is a partial order on A if it satisfies these three properties, that it's reflexive, antisymmetric, and transitive. R is said to be reflexive. We've seen this one before. If for every x in A, x is related to itself. R is called antisymmetric if for all x and y in A, if x is related to y and y is related to x, then x equals y. And R is called transitive if for all x, y, z in A, if x is related to y and y is related to z, then x is related to z. So the only difference between partial orders and equivalence relations is this number 2. Partial orders are antisymmetric and equivalence relations are symmetric. But that turns out to be actually quite a big difference, and in general, partial orders are not usually equivalence relations, and equivalence relations are usually not partial orders. And in fact, equivalence relations and partial orders are used for entirely different purposes. Equivalence relations are used to view different elements of a set as being in some sense the same by placing them in the same equivalence class, whereas order relations are used to compare elements of a given set as to their size. We're going to look at 3 examples of these things now, but the most fundamental example of a partial order is given by the following. If we give ourselves a set X, and we want to define the relation on P of X, the power set of X, which is the set of subsets of X. So we define S on the power set of X as follows. If U and V are elements of the power set, in other words, if they're subsets of X, we say that U is S related to V, provided U is a subset of V. If I'm using the letter S to stand for subset, then that turns out to be a partial order on P of X. So why don't you put your video on pause and see if you can come up with the proof of that. You'll have to prove that this relation, this S, is reflexive, antisymmetric, and transitive. See if you can give it a try. So here's the proof that S is reflexive. You have to show that every element of the underlying set, in this case of P of X, is related to itself. So you give yourself an element of P of X, and you have to show it's related to itself. In other words, you have to observe that any set is a subset of itself. And that's certainly true, and therefore S is reflexive. Now let's see if you can prove that S is antisymmetric. So antisymmetric means that if one element is related to another element and vice versa, then those two elements have to be the same. So you give yourself 2 elements of the power set. You assume that U is S related to V and V is S related to U. You have to prove that U is equal to V. Well, the first one says that U is a subset of V. The second says V is a subset of U, and therefore U is equal to V. Now let's see if you can prove that S is transitive. Here's the proof that S is transitive. We have to give ourselves 3 elements of the underlying set, so we give ourselves U, V, and W in the power set of X. We have to assume that U is S related to V and V is S related to W, and from that we have to deduce that U is S related to W. So that U is S related to V means U is a subset of V, and that V is S related to W means V is a subset of W, and we have to deduce from these two things that U is a subset of W, And of course, that's something that we've seen earlier on in the course. We've written a proof of that fact, so we'll just state it here. It follows that U is a subset of W. And so that completes the proof that S is transitive. And also the proof that S is a partial order. So in future, we're going to refer to the relation with this thing here rather than S. In other words, we'll just simply write U subset V. Here's another relation that I refer to as a fundamental example of a partial order. It's a relation on the set of natural numbers. We'll call it D, and D stands for divides. For natural numbers m and n, we say that m is D related to n, provided m divides n. Then I claim that D is a partial order on n. Let's see what the proof of that looks like. It's, again, very, very simple. Well, you give yourself an element of your underlying set, and you have to observe that it's related to itself. Well, of course, any natural number divides itself, and therefore that makes D reflexive. In order to show that D is antisymmetric, you have to show that if M is related, so you give yourself an M and an N, you assume that M is related to N, and N is related to M, then you have to deduce that M is equal to N. So if M divides N and N divides M, it's probably quite obvious to you that M must necessarily equal N, but I inserted, the details of the proof of that. Now, since M and N are both positive, that means the fact that M divides N means that there exists a natural number J such that N is equal to Jm, and there exists a natural number K such that M is Kn. So if you substitute this M for Kn, you get that N is equal to J times Kn. And now it follows just by cancellation that Jk is equal to 1. And the only way you can have a product of two natural numbers equal to 1 is if they're both equal to 1. And so looking back here, you see that N must equal M. And so that completes the proof that D is antisymmetric. And finally, we have to prove that D is transitive. So you have to give yourself three elements of the underlying set. You suppose that K is D related to L, and L is D related to M. So that means K divides L, and L divides M. So maybe it's obvious to you that necessarily K divides M, but here I've inserted the detailed proof of that. If K divides L, then there's a natural number X such that L is equal to XK, and L divides M, so there must exist a natural number Y such that M is Y times L. So now you just simply substitute in here for that L, you replace L by XK, and that gives you this. Well, since X times Y is an integer, it follows that K divides M, and that's what we wanted to prove. That completes the proof that D is transitive, and therefore that D is a partial order. In future, instead of using the symbol D to denote the relation, we'll just use our usual notation of that vertical slash to indicate that one natural number divides another natural number. By the way, you'll notice that if we view this relation that we've just defined as being a relation on Z rather than on N, it's not a partial order. Why is that? Which one of the three properties of a partial order does this not have if you view it as a relation on Z? Well, it isn't antisymmetric, you see, because just because X divides Y and Y divides X does not mean that X necessarily equals Y. For example, 2 divides minus 2, and minus 2 divides 2, but 2 is not equal to minus 2. Okay, so it's only viewed as being a partial order if we're defining it on the natural numbers rather than on the integers. Let me now give you another example of a partial order. We're going to call it LE. It's going to be a partial order on the set of real numbers. We define it as follows. For real numbers x and y, we say that x is LE related to y, provided x is less than or equal to y. It's really easy to show that LE is a partial order. It's reflexive because every x is less than or equal to itself. It's antisymmetric because if x is less than or equal to y, and y is less than or equal to x, then x is equal to y. And transitivity is just as simple to verify. So this is another example of a partial order. Clearly, I used LE to denote the less than or equal to symbol. The relation strictly less than on R is also an order relation, but it's not viewed as a partial order relation. It's not reflexive. Any element x is not strictly less than itself. In future, we're going to use the usual notation, the less than or equal to sign, instead of using the symbol LE. Now note that I didn't call it a fundamental example of a partial order. I just said that it is an example of a partial order, and that's because it has a certain extra property that makes it more than just merely a partial order. So that brings us to a new kind of an order relation. It's called a linear order, or it's also known in some textbooks as a total order. So a relation R on a set A is referred to as a linear order, provided it's a partial order, and it has this one extra property that for every x and y in the underlying set A, either x is related to y or y is related to x. In other words, every pair of elements are comparable to each other in one way or the other. So what's an example of such a thing? Well, the less than or equal to that we just talked about is what I would call a fundamental example of a linear order. If you give yourself any two real numbers, x and y, then it's necessarily true that either x is less than or equal to y, or y is less than or equal to x. On the other hand, this relation that we defined above on the power set of an x is usually not a linear order. Sometimes it is, but it usually isn't. If you, for example, take x to be this set, then these two are elements of the power set, and they're not comparable to each other according to this relation. This is not a subset of this, and this is not a subset of that. So in general, it's not true that this is a total order or a linear order. I say it's usually not a linear order, but sometimes it is. If you view it as being an order relation on this collection of subsets, in other words, we don't take the entire power set, but we just take this subset of the power set, then it is a linear order on that set, because for this particular family of sets, it really is the case that for any pair of them, one of them is a subset of the other. And finally, this relation of divides on the set of natural number is also not a linear order. For example, if you take the numbers 2 and 3, 2 and 3 are not comparable to each other using this particular relation. 2 doesn't divide 3, and 3 doesn't divide 2.